Section 2. Deep Reinforcement Learning with Deep Q Networks and Enhancements. Implementing a Deep Q network and applying target network updates. DQN's initial achievement was to get superhuman results on a variety of Atari games. The only inputs were screen pixels. The algorithm was general enough to perform well on a wide variety of games using mostly the same settings. The picture on the left gives the general setup. A video game screen inputs are fed into a convolutional neural network connected to a fully connected neural network, which then estimates the best action to take. On the right, you can see how widely DQN has been modified since its inception. At the middle of the image is the DQN, and branching off of it are a variety of algorithms that were inspired or built off of DQN in some way. We'll create a DQN in TensorFlow this section and continually modify it with TRFL. There are four main parts to a DQN. The first is Q-learning. The DQN trains on the same TRFL Q-learning function we implemented in Section 1. However, in this section, the input will be batches of tensors fed into a function approximator, i.e. the neural network. We'll be using the TRFL.QLearning loss output in a gradient descent optimizer to train the network. The function approximator in the original DQN was a convolutional neural network that turned the screen inputs into features. Those features were fed to a feed-forward neural network to estimate the action values. For those environments that don't have visual observations, like the CartPole environment we use in this section, the CNN isn't needed. The third major part of the DQN is the use of experience replay. As the agent interacts with the environment, it saves experiences into a memory buffer. The agent then trains on samples from that buffer. Experience replay generally helps off-policy methods like DQN be sample efficient and can prevent overfitting. The part of the DQN that we'll focus on in this video is target network updates. DQN has two neural networks, a training network and a target network. Remember how when we did the Q-learning update in the grid world example, we needed a next state Q value? In DQN, we use our target network to get the next state value. We update our training network with the next state target network value. Periodically, we replace the variables of the target network with the train network variables. Target networks generally increase the stability and convergence of algorithms. TRFL makes implementing target networks easy. TRFL also allows flexibility in the target network updates with the functions update target variables and periodic target update. Here's some sample usage of target variable updates in TRFL. We set up the train and target networks. We'll go over this step more when we review the code. Then we input the tensors into the TRFL method. In this DQN example, we use the train network variables, the second argument in TRFL.UpdateTargetVariables, to replace the target network variables, the first argument. In this session, we'll call the tensor operation to perform the target network update. By changing the tau argument, you can either fully replace the variables, tau equal to 1, or use a small tau amount to perform a partial update. The image on this slide shows a full target network update with the alternating blue and green blocks. Below that is the tau formula, which controls the degree to which the variables update. We input the target variables and source variables into the TRFL.UpdateTargetVariables function. The source variables replace the target variables based on the tau argument. Note that while we use this function for target network updating, the function can be applied generally to any two sets of TensorFlow variables. The function TRFL.PeriodicTargetUpdate controls how frequently we update the variables. Usage is the same as before, only we include an update period for how frequently the update should be done. Periodic target updates uses the periodically function. The function can be used more broadly to periodically perform TensorFlow operations. Note the update period is inverse frequency, i.e., if you want to update every fifth time, set this argument to 5. Periodic target update also has the tau parameter that controls how much we update the variables. We'll use the CartPole environment in the code samples for this section. In CartPole, you try to balance a pole on a cart by moving this cart left or right. If the pole falls below a certain angle, or the cart moves too far left or right, the episode ends. CartPole is considered solved if you can balance the pole for 200 consecutive steps for 100 straight episodes. In the Python notebook, we'll set up a DQN with the four main parts. We'll highlight TRFL usage like Q-learning and do 3 varieties of target network updating. Let's go over some code. The first few cells install TensorFlow and TRFL. The next cells let you visualize a few frames of CartPole. The agent tries to balance a pole on a cart by moving the cart. Here we implement the DQN and TensorFlow and TRFL. Since the CartPole environment doesn't provide visual observations, we're using a simple 2-layer neural network and not a convolutional neural network. Here we set up the tensors. We feed the input into the two-layer neural network and get the output here. This is the input going into the neural network, and here is the output. The truffle.QLearning function is the same as the one we saw last section. The only change in the inputs is that we use the output of the neural network as the first argument in the function. The output of the neural network going into the truffle.QLearning function. The output is a bit different than last section. We get a batch of tensors as the loss. We feed this loss into a gradient descent optimizer. Also note the getQNetworkVariables function. We use this function to get the variables to update the target network. Note the train and target networks are created here. We also set up some hyperparameters. The hidden size and learning rate parameters control the number of hidden units in the neural network and the learning rate of the optimizer. The update target every parameter controls how often we update the target network. In this case, we update it every 2,000 steps. The experience replay memory buffer is a queue. We add experiences, replacing the oldest one when it's full. We sample randomly from it when training the DQN. Truffle sets up the target network update operations in one line. Input the target variables, the source variables, and tau. We use the getQNetworkVariables function to get the variables we want to update from the Q networks. We'll show 3 different ways of updating the target network in this notebook. The first updates the target variables fully by setting tau equal to 1. For comparison, the rest of the cell includes a TensorFlow-only way of performing the updates. In the session, we call the target network update ops tensor. We call it every 2,000 steps. Also in the session, we perform some greedy actions by getting the output of the DQN. To train the network, we sample from the experience replay, get the next state Q values from the target network, and then feed these tensors into the session. Here are the results of the agent learning to play CartPole. You can see the reward gaining as the episodes increase. The rest of the notebook is largely the same. I'll focus on the parts that have the 2 different target network update operations. The next example uses update target variables with a small tau value, in this case 1 divided by 2,000. We are doing partial updates, so we can call this operation every step rather than once every 2,000 steps. Before, we were doing full updates once every 2,000 steps. Here, we are doing very small updates every step. The last example uses truffle.periodic target updates. In this case, we'll do full variable updates, tau equal to 1, every 2,000 steps. Note the addition of the update period argument. Here's the usage in the session. Here are some further resources.